Hello everyone. We are talking about geometric reasoning in Lean from algebraic structures to Presheaves. This is a project collaborating with Kenji from Yiming, France, and I'm a postdoc researcher in IMU Munich. So as for motivation, we are interested in interpreting formulas and proofs in a wide variety of mathematical contexts. Here, the fragment of our interest of logic is geometric logic, and the mathematical contexts are Presheaves categories, which are intuitively simply families of sets. And we carry out our formalization in the theorem prover Lean, which is a proof existence. As for geometric logic, it is a variant of first-order logic. There are a bunch of reasons to be interested in geometric logic. Firstly, it is expressive enough to capture the things of our interest. For instance, the several semigroups, monoids, deviation rings, and fields, and also linear orders, etc., are all geometric. And what we like about it is it is versatile. Means that it can be interpreted into a lot of categories. And critically, it is transferable, means the interpretation of geometric formulas are preserved by enough functors. Here, enough means that they are preserved by the functors we are interested in, which are geometric functor, if you are rather familiar with Grothendieck toposes. So we also have good reasons to do it in Lean. Firstly, Lean is actively developed proof existence with a large and active community of mathematician users. And also it is dependently typed, means that its kernel logic is rich enough for us to do this kind of formalization and will not hinder of our proofs. And we have a large library of mathematics called MathLib. And in particular, we have an existing library on category theory, where our work is constructed on top of. And finally, although we admit that we haven't tried anything on that fragment yet, we would like to bring up the potential of using the meta programming feature of Lean to use our formalization to construct proof tools that help us constructing more proofs as an extension of Lean. So to understand our project better, let me explain you what is geometric logic. A geometric term T generated from a finitely monocyclic signature sigma. And to construct formulas phi from these terms, we have atomic formulas, true top, bottom, and predicate symbol application on the terms, where the predicate symbol comes from the signature. And we have built-in equalities, we have binary conjunctions, and in contrast to first-order logic, we have possibly infinite disjunction. And also, different from first-order logic, we are not allowed to use the universal quantifier, but only the existential quantifier. And the theory is specified by axioms of the form phi1 entails phi2. Here, the turnstile symbol intuitively captures entailment. So as you can see here, there's no implication symbol available when we construct formulas, but effectively we can have one level of implication when declaring axioms. The limitation here is that we are not allowed to use nested level of implications on the left-hand side of the turnstile. So for the the simplest example, let us consider the theory of semigroups, which is an algebraic theory with only one binary operator, which is the multiplication, and no predicate symbols. So here in the signature, we have a tuple star2 capture. The star is a binary operator, and we have no predicate symbol. inductively, we can construct larger and larger terms using this function symbol. And our only axiom says top entails the associativity axiom. It is as simple as this. We are going to interpret this syntax on the structures presheaves. And to understand the presheave, what is a presheave? A presheave on category C is simply a functor from the opposite category of C to the category of sets. And the category of sets is just formalized as the category of types in Lim. More concretely, a presheave P on category C contains the following pieces of information. So firstly, we need a family of sets for each object C in C. And for each map from C1 to C2 in the category C, we require a function PF goes to in the opposite direction, which is from PC2 to PC1. And also for the first examples, a presheave on the terminal category is simply a set. In Lim, we can formalize it as the category of presheaves on the unit type is equivalent to the category of types, where the isomorphism symbol here is categorical equivalence. And as a slightly more complicated example, consider the category 2 pictured as two distinct objects and only one non-trivial array between them. In this case, a presheave on this category is simply a set theoretic function, goes from the opposite direction. As you can see, presheave on this category can be just the inclusion map from the natural number to the integers. So we are going to define a semantics on the presheaves. What do we mean by that? Well, by default, when talking about semantics, people mean set semantics, by which we mean a set model of a series T over the signature sigma consists of a set X with, for each n-array operation in the signature, an actual function from the nth power of S to X. And for each predicate symbol in the signature, a subset of the set, which is the nth power of X. And we require the axioms of the series T to be satisfied. So well, this slide also makes sense if we replace the word sets with the word presheave and do the replacement for function and subset accordingly. So in particular, by presheave semantics, we mean a presheave model of a series T or signature sigma consists of an underlying presheave X with, for each n-array operation F in the signature, a natural transformation between functors from the nth power of X to X. And for each n-array predicate symbol in the signature, a monomorphism to the nth power of X. And again, we require the axioms to be satisfied. So this semantics is what our formalization is based on. And here is our current contribution. Our new formalization is approximately 2,500 lines long, which contains geometric syntax, proof rules, and the definition of interpretation of geometric formulas in presheaves. We prove the soundness of the proof system we define for presheave semantics, and we prove that the collection of presheave models on any category C, where C is a fixed category, forms a category. And critically, we prove that this construction is functorial, and this is the currently hardest part. And why it is not working? So help. So by functoriality, we mean given categories C and D, and a functor F from C to D. And if we are given a model, which is a presheave of the series of series T in the signature sigma, then as a presheaf, M can be pulled back along the functor F to obtain a presheaf on the category C. And we have proved that the pullback is again a model of T. And this construction can be packed up as a functor from the category of models on D to the category of models on C. So this is what we mean by functorality.
Any kind of functor? Any kind of functor or just geometric functor?
This is yeah, we haven't. We just pack it up as a functor. No, we haven't shown that it has the adjoint property. We just had defined the functor itself. Yeah. So to demonstrate that we haven't messed up, we did a simple example which demonstrates our work can be effectively connected to the massif. We have proved that these following categories are equivalent. On the left-hand side is the standard definition, which is the existing notion of the category of semigroups. As we can see, a semigroup just consists of a carrier, which is a type, and a structure of semigroup on this type. And what we define is the series of semigroups. It has a definition as follows. You can see that it is in the signature of the signature with only one function symbol, and it has only one axiom. We define the category semigroup set models as the category of presheaf models of the series of semigroups on the type unit. And what we have to prove is that we have a categorical equivalence between the existing standard notion of semigroups and our construction of semigroup set models. So it means that our definitions is coherent with the massif. So this is basically what we have done. So what next? There are some immediate goals. Firstly, we are considering refining our work in terms of geometric category in generals, instead of talking about presheaves explicitly. This is because at the current point, we are not confident if the concreteness of presheaf semantics brings us more convenience or more pain in terms of type checking in Lean. So we imagine there might be some hope if we keep the abstractness to just working with geometric category instead. And moreover, we are interested in formalizing some interesting examples for interpretation of geometric formulas in interesting presheaf categories. So maybe some candidates include the category of simple sets, the topos of trees, or the classifying topos of a series of the presheaf types. And we are currently carrying out the generalization to sheaves, where sheaves is a further step of generalization compared to presheaves. Here, the sheaf, we mean sheaf on a side, which is the Gauss-centric topo stuff. And also, we have some long-term aims. One of our aim is to address some aspect of Bell-Schmidt thesis, which is application to algebraic geometry. And also, we are looking at the Lin theorem and the bar theorem, where the Lin theorem allows us to carry theorems about set models to other contexts, and the bar theorem will allow us to refine geometric proofs, so we avoid the axiom choice. So basically, it is that's it. And I'm not only reporting the progress, and I would appreciate the feedbacks from you. I would like to hear your comments, and I would like to hear your opinion, maybe as a user of other proof existence, ACTA or COG or whatever, to think about what would you guess to be difficult in our work, and how would you imagine if you are asked to address the same questions. And what information did you get out of our work? Is there anything surprising or interesting to you? This is what I want to deliver today. Thank you very much.